project on virtually 2-3 projects on macro grid also. They are not only solar, but we are integrating other energy also, like maybe wind and all that. But this is exclusively, we have a typically more than around more than 5 crore funding on this solar water pumping, like and then we thought it up. So anyhow, these are little data one can think about, like probably from MNRE side, so I can skip it. And then you can think about what we were using for the pump. We were using the grid. We were, of course, people start using the solar. I mean, people are also using the diesel, of course, DG sets also. I mean, like even a water pumping system, and like maybe a diesel or petrol or alternate any other purpose. Mainly the diesel pumps are there, like, and people are, of course, try in many places. I mean, for some pump, like maybe in windmill also. There, of course, animal. If you remember, it had been animal and then gravity and hydro and all those are there. So this is about the history, like. Why I've probably chosen in this, I started my career probably for motor design for, I mean, irrigation pump or agriculture pump, and probably I may be probably converging my career probably again from same water pumping system, but this is different technology than what it has been. I mean, including the motor design, like. So it's becoming today more and more relevant because the India is a country with the agricultural economy. I mean, and you can think about like a 52% total Indian force are probably in farm sector, and of course there are many reasons that why we have to probably. And you can think about the, if you look into the last portion, 25 million pumps are there in India, and out of that, still the 8 to 10 million pumps are diesel driven. I mean, like, and of course, the rest are driven by the electric supply also. I mean, like, so typically still one third or one fourth pumps are still with the DG sets, diesel engine driven water pumping system, like. I mean, so major challenge, of course, farmers are typically with the, if it is a electricity, then there is a frequent outage, and the another, of course, if they run a DG set, diesel, they use the diesel pump, then the cost of diesel is very high. I mean, like, so those are the reason. Then and typically this technology have to come up. Typically, I mean, like for especially for the farmer, not only for the farmer but many others, and we expect that it can probably save the diesel of around $6 billion in a year or so on typically on this segment, like. I mean, also. So this is the reason probably, I mean, one of the reasons that why the diesel subsidy have been there because of the farmers applications. Like this is one of the applications among the farmer where that people use, I mean, farmers use the diesel for that. Like. You can think about like typically, I mean, in 15, 16, 31,000, that's a typically old data. But if I come about like 91 to 2014, I mean, have been around 11, more than 11,000, around less than 12,000 pump have been there in the typically in 14 years. But in 3 years or 3 to 4 years, it has been 1.1 lakh pump, and these are also old data. Typically, might be now in last 3 years could have been probably double of that, more than 2.2 lakh pump. Of course, installed with this pump, water pumping system, like. Well, so this is considering that there are, of course, not only MNRE, but even the power ministry is after this. I mean, considering this, and the data may be a little old, and data go on changing. But more important is that this is one of the segment we can use the solar energy, which is locally can be generated and can be used for this kind of either as a terms of energy storage, or it can be used for typically for, I mean, the purpose of typically water pumping in many ways, like also. So this is, of course, I mean, like we think about like from the sun we can have. So the plenty of applications are there. Of course, you can think about of solar water pumps for irrigation and a sprinkler. So there may be many kind of technology in this. It can be like a simple. You have a similar like either diesel run pumps, or it may be electricity run pumps, and then you have a solar pump in the same way. Or you can have a spray irrigation also, as you see on the right side. I mean, like where the farming is also of different kinds, like maybe vegetable or any other product kind of things like that. Then you have a, of course, aqua farming. I mean, you need the water pumping for that also, or maybe a solar pumping for swimming pool. So there are plenty of applications where this you can call it the water pumping normally are used, like, I mean, water pumps are used, or maybe fountain. I mean, you use the fountain for typically for the garden or for many other purpose, or typically your domestic and municipality supply, which work very well because you have a overhead tank. So whenever the energy is available from solar, you can put in tank and later on can be given a water supply. So this is a good energy storage. I mean, because the solar is available in the day and it is little intermittent nature like because it is varying. I mean, if you are not connecting to the grid, then of course it is a good storage which one can think about like with the help of typically for municipality power supply. Where of course in India we have a normally because we don't have even a supply for typically water pumping 24 hours. Even we have a even like if we talk about in IIT system, we are not getting 24-hour supply. We are getting half an hour in the maybe morning and half an hour in the evening. Like, so it means it's coming from certainly some of the storage tank. So certainly, I mean, in the if whenever the solar is there, we can use for this purpose that we can we do the water pumping with the help of solar and we can store the water into the tank and then we can probably provide the water supply. So it's a one of the example where we have a very good energy storage in the form of like a water storage also. Like so you have a many kind of irrigation. You can just example some of the photograph. If you go to probably on the website, you have a which have come very recently. Even the banana crops in a place where nothing was grown, and people are able to put the panel all around the ground like a grid. And the kind of banana which are not, I mean, the crops which are not affected, probably when you have a little shadow of the panels also like also. Or typically leverage stock for fish tank. So I mean these are the some of the typical or the RO system or like a civil, industrial or typically municipality or so many applications like. So these are the some application I wanted to just tell you about the applications, but there have been a many variants like what you can think about with the solar generation. I mean, like maybe one is that once you install the panel, then you would like to have a maximum power from that. The concept of maximum power tracking is there. Sometimes we need not to have a maximum power tracking. I mean, like maybe, but most of the time, of course, we not like to do the energy generated or from this whatever the investment we made it like. So there are many variations. I will just come to that because you can use the I mean, many even typically what we are working typically with the 5 motors like and of course this is a little bit economics like how it look like because it's a local generated, not to probably typically go ahead like. So in the solar, I think most of you might be exposed a little with the solar. We have a concept of maximum power tracking like here if you look into it is a IV characteristic and you would like to operate here the power is maximum as you see in this characteristic where when the your solar insolation or you can call it sunlight intensity changes, you'll find the power is also changing. So you like to operate all these characteristic all the time in that so that you generate the maximum power, whatever is the typically your solar energy available at particular instant. So it is affected by solar intensity. It is also affected by the temperature. I mean, like of little bit affected by temperature, but of course we don't presume that it is too much affected by the temperature. But certainly with the solar intensity changes reasonably. Like so, power level will go on changing in the daytime. So it means this is a very interesting problem which I asked I mean, some of the students for working on maximum power tracking. I mean, like it's a dynamical optimization. It's a single variable optimization problem, but it's a dynamically changing optimization problem. So all the time, morning to evening, you will find. I mean, it go on changing. Maybe clouds may be there. I mean, you may find even the partial setting is also there in some cases. But otherwise, if it is also not partial setting, but you might have. I mean, the typical example like maybe the especially the clouds and other things. So those things may happen, of course, like in this solar like. So now coming to the exactly the typically the topic like what we have. Normally you can call it either PV panel or you call it PV array, photovoltaic array, and we have some kind of a power converter. And from power converter we feed to the motor and pump. This motor pump can be, of course, maybe I mean on the ground, or it can be like a typical example, maybe it may be submersible pump. Most of the time, it is a submersible now. There are many reasons because submersible pump are more efficient. That is one of the reasons because the cooling is better, and for especially for irrigation or even for the drinking power supply also. Typically, there is no question of the theft or something like that. But very important reason is why motor is more efficient because you can have a long stack length of the motor, and inactive portion of the conductor can be reduced in this motor, and cooling is better once it is submerged into the water. Of course, there are many technology. Earlier, we were having a perception that farmers were using the motors of 6-pole motors. I mean, 960 RPM with the belt pulley arrangement. But that was the time when I was doing PhD around 1980 or so. The concept gone to of monoblock. Monoblock means it's a four-pole motor of 1500 RPM, especially squirrel cage induction motor because it's the cheapest motor, and submersible motor concept start coming like. But even the, I mean, we are not the people in the area of water pumping or pumps especially. But when we came to the close to the industry, we found now they are using the pump even of not a 1500 or 1450 RPM or 1460 RPM. They are using the pump normally now around 3000 RPM. And the pump is also of another category, not only centrifugal pump, but they have a volumetric pump and even a hexical kind of pump, which give a very good efficiency. I mean, they claim that efficiency even from 35 to 40%, they are able to increase around 60 to 65% efficiency of pump also, which we consider. But those kind of pumps, they have optimized corresponding to around 3000 RPM. So if you mean to say that like we have to run this motor typically about at 3000 RPM, and now you can understand the water pumping when I have seen probably in the ground level that the water pumping is start by the most of these pumps when you start running these pumps from around 1100 RPM. I mean, many of you might, I don't know whether you have seen or not. So you have a very wide range that you can change. You can change the if it is a standalone system, you can change the water, I mean, delivery, or you can call it the, I mean, the delivery of the water pumping by varying the speed over a wide range, starting from 1200 RPM approximately up to 3000 RPM. Because I mean, they claim like at 3000 RPM, I mean, the pump as well as pump give a very good efficiency, which we are having from electrical side, considering that with the mechanical component might have a lot of losses on high speed, but it's not true. They have a better pump which runs at 3000 RPM. So we have wide, very wide range of speed. Why I'm talking about wide range of the speed? Because solar intensity from day to evening, morning to evening may change if you have a standalone system. But of course, there are many concepts like you may have a grid interface also along with that. We will discuss that also. So what I mean, like if you have a standalone system, you have a PV array, then you have a power converter. It may be single converter, or it can be two converter. If it is a two converter, we call it two stage. If it is a single converter, we have a single stage. Then you have a motor and pump. The motor also may be a lot of variety. And normally, some of the motors have a similar kind of converter, like you can call it voltage source inverter or converter or voltage source inverter. But many motors, like which I talk about, like a switch reluctance motor, it does not have a similar kind of inverter, but it has a different kind of inverter. And then might be having another converter, which a DC-DC converter at the input for responsible for maximum power taking, or you can have a single inverter itself, not necessarily the two converters. Like so, many cases, of course, there is a some benefit, advantage or disadvantage, and you have, of course, in maximum power algorithm here, as well as you have to adjust the speed of your motor and frequency, of course, by varying the voltage and frequency. You have to adjust typically how much the energy or power is available in the external system. But if it is a grid interface system, you can take the remaining power from the grid. And of course, now the concept is there when government of India is pressing hard that you can have a farmer income, I mean, to increase. They have a lot of areas in their, I mean, the farm field, or even in a Dinker power supply, you have a tank. You might have seen there is a reasonable area that you can put a panel rating or solar PV array of larger rating, and some energy can be utilized. Of course, power can be utilized for water pumping. Remaining can go to the grid. And of course, it's a net metering is already approved, so you can feed the power to the grid in the day, part of power, if you have a more generated power. And maybe in the night, for if you want continuous uninterrupted water pumping, you can take the power from the grid. Like so, those kind of, I mean, the configuration or, I mean, schemes also we look into, like. Well, when we talk about this PV array maximum power taking, you have a lot of techniques, and reason I told you, like, it's a very dynamically single variable optimization problem, but a lot of all the time the problems is going changing dynamically. So it's a very interesting problems practically, and probably around 5 years back, I think 4 years back, I asked one of my PhD students, I mean, like, to work only on MPPT, and he came, of course, with a lot of algorithm. I mean, like, but I just asked him to take a simple platform of for the purpose of putting this kind of control algorithm, especially for MPPT, like also. So you have a lot, and you can look into the most popular are two, like we call it perturb and observe. I mean, like this is typically the flow chart, but the basic concept is on that characteristic how you are moving towards the peak point. Like, I mean, I retain the peak point because peak point may go on changing because of intensity change or partial setting or many other way. I mean, weather condition maybe or something like that. Or there is another technique which we call it incremental conductance. So these are two very popular, and there are a lot of modification of these two techniques in practice. So I will not devote too much time on that. Probably if you really want to work out, you can probably work out within a 1 or 2, I mean, hours. You can easily understand and model it for your requirement also. Well, there are, I mean, these are the issues like one can think about about this MPPT, but you have to use one MPPT, which you can think about So you can think about when we look into literature, so many kind of MPPT are there already put into the literature. By my student from some of the literature Now this is about the solar MPPT. We'll use it that, but now the question is these are the typically 6 motors, and this initially first was the DC motor. I've seen this DC motor was initially used with a permanent field on stator, which in 92, Pumpin, Gloucester Brothers and BHL, they were developing. I mean, this was the first phase in 92. They were using a permanent brush DC motor. The reason being, they consider the DC motor. I mean, if it is a permanent brush DC motor, not to have a field excitation or control, but only armature voltage power was going to armature, and not to have any control. And they were modifying even the characteristic of. They don't want to put any electronics virtually into it, and they were modifying the characteristic of the pump itself so that most of the time it runs on MPPT. But the reason being this, even if you put a permanent in DC motor, that can be on stator, but still you have a brush and armature. So that has a still maintenance issue, and it cannot be gone to as a submersible pump. I've gone to Central Electronics Limited. They were also developing probably in typically in 84 or 80, typically around 90 or so, 92 or so. They were mainly having such kind of pump, but they started looking on induction motor. They were having 1 or 2, I mean, set of induction motor or something like that also. But what I will be talking about, like all these 5 different motors, which you can think about as a brushless. The induction motor, especially the cage induction motor, is the first motor which we consider as a benchmark. I mean, like to compare all. Well, it is normally used now in with the electric governed water pumps. This skull cage induction motor, they are used. And once you install, you forget about quarter century. Like the life considered around 25 years, provided you don't abuse. Abuse in the sense that you don't run balance. I mean, or there is some failure on mechanical side or something like that, and the pump can run for probably quarter century. Of course, we will consider if technology changes after reasonable time, then you have to really change this. But in this solar pumping, certainly we can't run the motor, these motors directly with the supply, because you have a concept of it's a DC supply. So we have a concept of MPPT, as well as we have to convert this DC into AC supply. Of course, we have to use some kind of inverter or converter concept. So I'll be talking about starting from induction motor, then the brushless, permanent brushless DC motor, which is considered to be one of the reasonably good efficiency motor. You can think about in your floppy disk drive, hard disk drive, even the 5-watt motors have around efficiency more than 90%. So now application not only computer industry, but you have like a ceiling fan. You have like a 35-watt or 30-watt to 35-watt ceiling fan with a BLDC motor, where even like a order of 30 to 35 watt, it achieves the efficiency around 80% or so in the fans, where induction motor have a 30 to 35% efficiency. So going to be formed conservation in this motor. So it started coming earlier. These motors were costly, but now you can think about this is the motor also rule another your electric vehicle called e-rickshaw, and you can understand probably your neighboring country e-rickshaw controller with a motor around of 1 kilowatt, they are offering only in 6,000 rupees. 6,500 rupees, like even for 1 kilowatt motor. So the cost, I mean, when you talk about the cost of this motor has gone drastically down. Like typically, as far as the motor and dedicated controller for particular application, even if you go to like probably about 1.5 horsepower induction motor to go to market, you'll not get less than 5,000-6,000 rupees. And here this motor is with the controller, because they are producing in the bulk, and application you can think about like a 2.5 crore e-rickshaw on Indian roads. So this rule and control is quite simple, including the sensorless control. So this motor also will be talking about. Virtually, I put probably 2 PhD students in 92 one, first one, and second PhD student. Of course, first he graduated already. I mean, couple of years back. Like, so we'll be talking about this, and another student is working, of course, from who is interfacing with the industry also. And another motor which I'm working like a typically the switch reluctance motor. I mean, we'll talk about this switch reluctance motor also. I mean, we develop and not only this application of water pumping, but our students are working for other applications also. Then we will be working like a synchronous reluctance motor, which we are very keen. I got it developed even at undergraduate project as well as postgraduate thesis and University of Roorkee in like 1986 to 88. Got it developed this motor, but it's a very raw motor. That time we developed it, but we were very keen to procure this motor. We couldn't get it. Of course, we procure very bad quality motors around like a 8 year back from some company from Pune. But what they remove only, I mean, part of the cage and claim that it's a synchronous reluctance motor, but it's basically was a conventional squirrel cage induction motor, and just remove the fee of the bars and cut in a way that it gives some saliency on that. But now the motor which I was going through some of my students probably around 4 or 5 years back, that this motor have to come. But when they saw it, they say that ABB and Siemens already launched like around 4 years. This motor with very interesting configuration, especially called ALA construction with the flux barrier. I will show you the photo. Even we also got developed this motor by the industry with whom we are working on the project. Like, I mean, so this motor is also very good motor. It's better than induction motor in efficiency. Of course, power factor may be some little bit issue of little lower side than induction motor, but certainly we are not connecting this motor with the supply, AC supply. We are feeding from inverter, and we can optimize this motor even for field excitation system also, which I will talk about when we will come to this motor. Like, so, but I mean, like, it's a very fantastic motor, going to be a lot of applications, and we procure around 4 motors from ABB. I mean, typically with the controllers, and students are working for not only water pumping but for other project also using synchronous motor. But it's a very good motor. Like, I mean, I can tell you about efficiency and also another motor is like a PMSM, permanent synchronous motor, permanent sine fed motor. Like you say, another version of permanent motor where we put the magnets on the rotor. Like also, yeah, earlier people were preferring the BLDC motor. I mean, permanent brushed DC motor, because the sensorless operation was very simple. But in last 5 years, the sense certainly better. Use also like a typically like your electric vehicle PMSM. For large rating, PMSM are used, but of course lower rating the PMLDC, like e-rickshaw is a PMLDC. But large rating, if you talk about like maybe the electric car, four-wheeler, I mean, like typically the Tesla from induction motor, they are also going for some of the, I mean, like motors in PMS category. So there are plenty of examples where PMSM is coming up a little larger rating, starting from a couple of kilowatt or higher rating. Like, so we consider that all these 5 motors investigate on the control as well as the development of motors. So how we go now? This is typically we talk about like starting like one is like a position sensor. We use it in that. So it's an inverter fed. Another is like we can use the position sensorless. So final product have to go with the position sensorless. Because in submersible pump you cannot put the position sensor. Even if the reason being, there are two reasons. Some of the position sensors are very costly, especially for PMSM. I mean, or even a reluctance motor. I mean, it's a very costly and it requires reasonable space also. And moreover, in submersible pump, it's a big issue because motor may be submerged into the water. Typically, submerged into the water, maybe 100 feet, 200 feet down. So you cannot run the. I mean, other than power cable, if you run another encoder cable or sensor cable, cost will increase. I mean, like, and many issues. So what is preferred now in all these, the sensorless, like, so we also work on sensorless. So another options may be like you can think about whether it is a standalone system or along with the PV you have a grid interconnection also. So we'll be going like in standalone, double stage and single stage, and then grid connected also we have a two concept like unidirectional power flow and bidirectional power flow. So unidirectional power flow means we are taking a power, of course the power uninterruptible water pumping we are taking from the grid. Okay, in unidirectional power flow. But in bidirectional power flow, the concept is you can take the PV panel size higher. As I was talking about that we want to increase the probably the income of the farmers now. So he has a lot of area or catchment in his farm or field or even in drinking water power supply, you may have a reasonable area. You can install the panel of higher size. And in agriculture, some of the agriculture crop, like a banana, I told you, you can put the panel probably in the whole of the field, like and you can generate much power, reasonably larger power than the rating of pump. So remaining power can go to the grid, and you can have a water pumping, so that you have a concept of net metering. You can sell off electricity also from there. Typically, it's like a similarity like a grid connected solar system also, and you have a water pumping also. So that's virtually the concept we have worked also on that, like or something like that. Because the electricity generated by solar is very cheap. Like at the moment, it is 2 rupee 34 paisa, where the grid supply what we are getting in an IIT is a 10 rupee 25 paisa. You can think about it. A grid power supply is a 4 times costlier than what we are generating locally from the solar light, and it still probably it might go. Maybe in next 4 5 years, it is around like a 1 rupee 25 paisa per unit of the electricity generated from solar. Like, so in that case, the farmer can earn the revenue by putting the extra power. He can put more panel and can then sell the electricity to the grid, and of course, he can run the pump uninterrupted 24 hours. Because many crops are there, you have to give the water continuously. You cannot give the water only for the short period and then you go ahead. Well, coming to typically the first category of, motor for water pumping is the squirrel cage induction motor. And most of you might be probably all aware already. I think you have gone the 3 days or more than 3 days for this FDP program. Typically about certainly there may be some already lecture for variable frequency dive on using induction motor. So what will be, you have a three concept virtually here for variable frequency or variable speed drive for induction motor. The one is called it scalar control, or we call it V/F control. And there are other two concepts like called vector control as well as direct torque control. So we use all three, of course, typically with a couple of master student. I think probably couple of master student as well as like some different effect like so this is simple one. Our this master student along with the typically one of the PhD student, he work on this scalar control. We call it scalar control. It was a very simple concept. Initially, it couldn't work out. I have to give very high cost processor, and finally, he's able to develop it for the industry of the simple DSP of like couple of thousand rupees only. And of course, it's a sensorless in the sense we are not because it's a scalar control. We know to sense either the speed of the motor, we know to sense the motor current, okay, or winding current. We know to sense inverter current. What we are sensing here, we are just sensing the DC link voltage as well as only sensing the PV voltage and PV current. And this is the very extremely simple control, the concept which I told them how it can go. The reason being induction motor, we are using a boost converter for MPPT. In this approach, and another control concept here we are putting that we should maintain the DC link voltage. Because the induction motor certainly we run an inverter, and the inverter will run very satisfactorily if you maintain this DC link voltage constant. Like so, in this concept, a very simple concept with this color control, what we did it, there may be a kind of buffer between the two, that the boost converter do the MPPT, and the DC link voltage is controlled by another control by adjusting the speed of the motor. Like if more power is there, you should increase the speed of the motor and pump is more, so that it is able to consume the more power which is generated by solar, because it's a standalone system. So we have to regulate the DC link voltage, okay, because it will regulate the DC link voltage and operate the inverter very satisfactorily. Like so, by adding these two, we get the reference speed, and from reference speed we get the frequency, and from frequency by this V/F control we get the voltage. So once you have a reference voltage and frequency, you can have a three-phase sinusoidal waveform of variable voltage, variable frequency, according to like of course this MPPT control and probably the frequency corresponding to that. And with the sinusoidal modulation, we give the getting signal to voltage source. So in this case, DC link voltage is regulated. We get the MPPT also, and it runs at the different speed. Speed is decided by how much see the PV generated power. If PV generated power is more, speed will be more. PV generate only initial issue with the student, they have to make sure with the right working. I mean, like typically with this scheme, I given a simple concept to student like to work out. I mean, with minimum sensors, so we have a typically here the 2 voltage sensor, one on DC link, another voltage sensor on PV panel, and only the PV current, no other sensors in this system. You can understand only the three sensors, 2 voltage and one current, and system work very satisfactorily without any problem. I mean, on motor side there was no sensor on inverter side like that. On that. So initial magnet and even industry we work on the of course 0.5 kilowatt panel like that. In lab product we have like around solar simulator, so we can probably PV and we can have the motor as well as the couple. Of course, the MPPT solar we are able to run at almost like 100% efficiency. I mean, So which slide I was there, like a 36? You are able to say,
Yes, sir.
see it like, okay. So which slide I should start with? Where I was, I mean, I'm not, I'm sorry, you will be able to give a feedback. Which slide I was there? Can you tell me the which
30,
slide?
30, sir.
30.
30th number.
So we were here, from here, like,
Yes, sir.
okay. Yes, sorry, anyhow, I'm like, oh, well, I think I was explaining that it's a two-stage system. Voice is coming all right, like something like that. Hello? You are able to hear properly
Yes,
my
sir.
voice? No.
Yes, sir. Yes, sir.
Okay. So if it is there, then you can call me on phone. There is no problem. I have a mobile here. Okay.
Yes,
So
sir.
anyhow, I was explaining it is a two-stage system. So we have a PV array, then we have a boost converter for MPPT, and we have a voltage source inverter fitting induction motor drive, I mean coupled to the pump. This we have a scalar control. So what we do with the MPPT, we get the typically the by operating MPPT means we give the typically duty cycle of the boost converter, and we of course from we have a voltage and current, so we have a power, and from power we get the one corresponding term, call it like from affinity law, the one reference speed. Another component we get from DC-link voltage control, which we want to maintain a constant voltage so that inverter works satisfactorily. So we get another term, and then we get the reference speed here. And this speed we convert to frequency, and by V by F control, scalar control, we get the voltage also. And then we from voltage and frequency, once we know, we can generate three-phase sine wave for sinusoidal pendulum for this inverter. Like, so the benefit of this system is that we don't have a speed sensor, we don't have a current sensor on the motor side. It's a very simple control. And well, depending upon the solar intensity, automatically the frequency as well as voltage and speed of the motor is decided as much power as pump can consume. Like, I mean, also, of course, this work was probably published in industry application transaction. Like, I mean, also, this is the rating, and this is MPPT. Corresponding to, we are able to get the MPPT, I mean, like 100% for, I mean, varying intensity. And this is the starting characteristic of this, which already I was talking about, like how motor is starting. I mean, dynamic response may be like a, it can start like depends on inertia, 5 to 10 seconds. It does not take much. It's a variable frequency starting. The motor is very safe that you can limit the current not going to be more than particular amount of the current into the motor. Like it's an inverter fed. Like, so you can set the dynamics corresponding to that. Like, and these are the steady state result, of course, at 1000 watt per meter for like a motor current, then boost converter, I mean like parameters, solar parameters, and of course the net like a PV voltage, DC voltage, and typically motor current and motor speed, just to give idea. And this is during dynamic condition when solar insolation change. The dynamics here is not a major issue because the insolation does not change so fast. Like, so the control is able to take care without any problem whether intensity reduces or intensity increase. Like, and of course that was the double stage system. We call it two converter. Here it is a single stage converter that we eliminate the boost converter. Okay, the cost goes down. We reduce the one sensor also, DC-link voltage sensor, because now it is a PV voltage is the DC-link voltage, so we are able to get MPPT, and from this directly we are able to get it the frequency, and we get the voltage from scalar control and sinusoidal modulation. We run this. So benefit is that we remove the one sensor as well as we remove one converter. But there is a penalty that now the PV voltage have to increase, and during MPPT also this voltage should be in a way that the motor should run satisfactorily. Like, so still the voltage should not go very down, otherwise you will not be able to implement V by F control of this. So still the system work without any problem. So this is a little modification in MPPT. Directly from MPPT you will get the frequency of it as it is shown the previous block, and typically you, I mean, like from frequency you can get the voltage, and then so we are able to run this also satisfactorily. And this is the starting performance. You can just see initially it is open circuit voltage, and then the voltage goes, PV voltage goes slightly down when it goes towards MPPT, and the current also increases, PV current that give a, and of course the motor current also increases when it comes to final speed, as the you can see from this. So this also run very satisfactorily. Only that the design issues are there, some limitations are there. There you have to select the device of higher voltage rating and utilize that little lower rating, like also. You have to select the device like IGBT on open circuit voltage of the PV array, but utilize them at corresponding to the MPPT voltage also, which is always low. Like these are the, of course, the steady state result corresponding to 1000 and typically in top 1000 watt per meter, and this is 600 watt per meter square. Like winding current of the motor and PV voltage, PV current, speed, current, motor current, so like. So it works very satisfactorily, and during dynamics also, if intensity reduces or intensity increases, it runs without any much problem. So that is about typically the your scalar control of both kind. And now we go typically like a concept of vector control. You can just see here how typically the vector control is there. Here also we have not increased so many sensors. Virtually we reduced now, it's a single stage system same which I took about. But we have gone now with vector control. So we have here the voltage sensing on DC link, which is PV voltage, and we have a winding current here, like also. Typically, of course, I think we have a current sensing also on PV. Of course, here PV voltage and PV current from which we put MPPT, and when we get the reference speed from here, and of course from the current and from DC link voltage. From DC link voltage, we calculate the three-phase pendulum voltage here. From pendulum, we get the alpha beta transformation, and from this voltage and current, we are able to get the flux. Typically, the flux and the magnitude of flux component and angle, which required for vector control, and we are able to get like a VDVQ from typically from these voltage and IDIQ also, and we estimate the slip speed as well as we estimate the synchronous speed from which we estimate the rotary speed. We are not putting a speed sensor, so we are estimating the speed. We have a reference speed, we put a speed controller for vector control here, and corresponding to one speed controller, and we have a slip frequency. We are able to execute the vector control to get three-phase reference current by using indirect vector control. And we have already sense current. The motor is star connected to sensing it to RNF, and we are able to current controller here. You can put any current controller, it's the simplest one, and we are able to give the gating signal here. So what I mean here, without again the speed sensor and having a like only typically taking only one voltage sensor, but typically three current sensor, we are able to operate in vector control. The benefit of vector control is compared to scalar control that we don't have any stability issue. And here the motor is also more safe in the sense that we are not, we are putting current control also in the vector control. The current is controlled here because you are sensing the current and controlling the current. So the motor will be safe, that current, our inverter is also safe, current never exceeding even during dynamics also. And it works as a linear plant similar to DC motor as vector control. Many of you could have gone through last 3 days or so, especially on induction motor. I hope you might have already some lecture on vector control too. We only apply for this, typically for this application. So this is your typically the MPPT. We got like almost like 100% MPPT in typically again on both solar and solar cell level. Of this system, and this is typically the starting. So you can just see the very clear starting, the speed of the motor, the winding current, okay, and typically the here is the PV current. Starting from 0, it goes to and PV voltage, which slightly reduces once the motor start consuming more power when it speed increases, because pump will be putting more load on the motor. And this is steady state corresponding to 1000 watt per meter square. Similarly, corresponding to when you have a insulation varying from 1000 to 500 or 500 to 1000 to dynamics is also quite satisfactory. In this case with typically this vector control So that's about typically the vector control concept. Like here, the concept is typically here of DTC. I asked my student, this PhD student, to work out with the same concept but using the DTC. And in this DTC, you can typically understand, like here, we have MPPT with the, because this reference voltage coming from MPPT, and we have a sense DC link voltage. So we have a typically the voltage controller, which of course will give MPPT, but similarly reference speed from this will be coming here, one from the DC link voltage, another is typically coming from DC link voltage control, another is coming from power. So we get a reference speed, the concept which I have given earlier, and we have an estimated speed from DTC. Okay, so we have a speed control which give a reference torque. We have a estimated torque. We have a corresponding to field weakening also, the flux, reference flux, and we have an estimated flux. And using this your stresses on torque as well as on flux, we are able to get a TOS, voltage switching for direct torque control. Direct DTC control for this this induction motor. the user will not be able to know whether vector control DTC because you are putting same number of sensors. And we are putting PV, the voltage sensor and current sensor and two current sensor. We are able to get the direct torque control also, without any problem. So that's about the MPPT corresponding to PV, and this is the corresponding to the starting. Of course, DTC give a little faster response. Because you can build up the torque at very fast in this case. And this is a winding current, the motor, typically the PV current, PV voltage, and of course your speed in that, and under steady state at 1000 watt per meter square. And this is of course the dynamics, when you have insulation changes, how the dynamics is there of this motor typically going on. That's about the typically all the three control and one can extend to. Now this is we want to have a grid interface. If motor is of typically up to 3 to 4 kilowatt, like maybe a 3 horsepower motor, order of that 2 horsepower, 3 horsepower motor, then we can interface with the grid also. And we have a solar also. So the power which we are taking from the grid is just supplementing along with the solar. Because solar power may go on changing, so we can run pump at the constant speed and discharge the constant water supply. Because some power we can take here, remaining power we can take here. And in the night, of course, we can run with this alone from this boost converter. So here also we took in a way that we took a boost converter so that power factor correction is there and current unity power factor is achieved in grid side also. Along with of course MPPT, we take care of this huge fully, and remaining power we take from the grid. So that's the concept for unidirectional power flow. For lower water pumping system like 1 HP, 2 HP, 3 HP, even up to 5 HP, we normally use the single phase grid for that purpose. So here also, of course, we are able to use it now. Now the DC link voltage is typically can be controlled by this grid. If grid is up there, and if grid is not there, it goes into the same control mode as we have a single, typically standalone mode. I will discuss the first scheme. Because this system, if you go on adding this feature, it means we will have certainly the more mode of operation. If grid is not there, still you can operate with, of course, whatever power you generate. From that you can run this pump also. So this is the concept how you the converter, boost converter. You have a template of it, you have a current of it, and you have a typically reference current, you have a sense current of the typically inductor, and you have a getting signal for boost converter. But of course, from this DC link voltage output, similarly what we were doing in case of this, we have this and we have a maximum power. So from this we are able to get frequency and we are able to run it successfully from starting for the same scalar control. Well, these are the same, the 3 HP motor, we tested design and tested the concept. And of course, we are able to operate which I already talk about. You can run only with the solar. If grid is not there, you can run only with the grid in the night when solar is not there. And when both are there, you can run, of course, sharing the power from whatever the power from solar PV, and remaining power can come from the grid. So the first mode with the boost converter. Okay, grid is running it, so you can just see the supply voltage and grid current, and then you have typically the grid voltage, current amplitude, and then typically motor speed and DC link voltage. So once you are running the grid with the boost converter, it's able to come to a regulated voltage of DC link also. So with the grid is a normal supply, but of course it is an inverter. You can have a soft starting with variable frequency. You can just see it's a variable frequency starting, so that the inverter remains safe, motor remains the safe. It's a virtually you are running the motor. Maybe the grid may have some voltage fluctuation, but the converter takes care that the motor is quite safe and run with the control current And these are of course the waveform of boost converter, supply side converter, and typically the winding currents and all those 3-phase winding current. And of course the power quality means we can think about the power factor is close to unity at different power level. Unity power factor as well as here on both when you run typically under, because voltage not under your control, the voltage might vary, but you can think about that typically at lower power, lower speed you want to run, a higher speed you want to run. It runs very effectively So that's with the grid supply. And then third mode is when you are running with the both. So there is some solar intensity, some power is coming from solar, remaining power coming from the grid typically. So this is a grid voltage and grid current. I mean, because some power is coming in this case, and when your intensity is increasing, like probably you are taking less power from the grid. I mean, you can see the grid current is reduced like in that also. So, and you can just see when intensity go on changing, the grid current accordingly go on changing. This is a grid current. When solar intensity is reducing, so remaining power have to come from grid, so grid current is increasing. When the typically the solar insolation increasing, the PV current increasing, and accordingly the grid current go on reducing. Grid voltage will not be affected, but grid current will go on reducing. So they go on sharing the power. I mean, accordingly the available power from the solar insolation. So control takes care, and here also the power factor is almost like close to unity, and TAD of the grid current is around like less than 2.9% or 5.7% or something like that from the grid. So that's about MPPT of the solar. And you can just see at the solar radiation, if it is full, you take maximum power of this. As the radiation reduces towards zero, it takes the power from the grid. So this is the sharing. Red is from the grid, and your blue is from the solar. So they share the power so that the pump run at constant speed with the constant input power as far as pump is. This is another interesting case when you have a high power rating of this motor. So then we have to go for three-phase grid. And now three-phase grid means we are putting three-phase voltage source converter. And of course, here we have a boost converter from solar. So we regulate the DC link voltage. But who will regulate the DC link voltage? When the grid is there, solar is there, this converter should regulate, this voltage source converter should regulate the DC link voltage. So if more power is there, which pump is not consuming, this power by regulating this, it will go to the grid here. I mean, like automatically it will come. When you have less power, it will take the power from the grid. Whatever, I mean, the solar is not there. So it's so. I mean, now this is a bidirectional feature that can feed the power from the solar extra power. If pumping is, there is no pumping or your generation, the power goes to the grid in this manner, in that manner. And of course, if when you have a solar less and you want to run the pump at, of course, at constant speed at constant power output, you take the some power from pump and from the solar and remaining power from the grid. Let's say this. So you have a many mode. The power goes to the, I mean, pumping is there. Power goes, some power goes to the solar to the grid. Pumping is not there. Then also power goes to the grid. And then there is no solar. Then you operate from this grid. And when, of course, less power is there from solar, some power from coming from grid and some power come from the solar light. So these all modes, four modes we have operated the system. I mean, like, but of course, this is very interesting feature where the panel size may be more and you can put the power to the grid when pumping is not there, or you can pump along with the running the pump, you can feed some power to the grid and you can have a net metering. You can earn the revenue. Farmer can earn the revenue by generating the power and putting to the grid along with running his own pumps, like in that way also. So this is a concept where the farmer income can be raised from this because he might have a enough area for putting the solar panel, like, and now the solar energy is quite cheaper than the grid, so he can sell at typically much higher cost what probably might be generating from here this system, like. So this is a typical concept like we thought of putting to the grid, and this is of course the control how it is goes by DC voltage control. You feed it like active component of current, and then reactive you put zero on the grid side. You have three-phase reference current, you sense the three-phase grid current, and have a control of voltage source converter on grid side like all. But DC link voltage control will have a bidirectional power flow, which I was talking about. It will take care of this, and of course you have a power component and DC link voltage regulation. And if grid fail, it's automatically take care and it runs. Typically, even with the scalar control, it runs the without any problem. This your water pumping system like also. Of course, all four mode with only solar array, with only grid, with both power is fed to the pump like from both, or when typically you can call it power is fed for pump as well as to the grid. So different modes can be there. Of course, I mean, like you can, I mean, I explain it all four modes, which are typically four modes. So these are the typical result with only solar is there. It's similar to what we already explained earlier, and the steady state result, and of course dynamics of it. And then mode two, when typically you are taking some power from the grid and some from solar, and it's running satisfactory like coming, and you have then typically one even a less than 2%. I mean, you can think about like a less than 2% air in. They're able to get a good power factor, like typically of around unity power factor. You can just see in the power as unity power factor as well as here. I mean, like in power, almost like a unity power factor in this side. Like, and these are of course the steady state result corresponding to that. Also on mode 3. The mode, typically the mode 4 is when you are feeding the power to the grid and running the pump also. Like you, because you have a more generation, you have design in a manner as fitting to the grid line. So that's the case. You can just see the typically here the grid current is out of the phase from the grid voltage like also. And of course it's solar insolation level changing. So how did changing the phase sequence of the current? Like when solar insolation was less, I mean the power was coming from the grid, and when the solar insolation increase, the power start feeding to the grid. So it changes like a typically you can think about the phase of the current. I mean corresponding to. I hope it should be in a large waveform. Here you can have a reflection of that, how it looks like that. All these are the experimental results we, of course, on laboratory prototype we run successfully. So here also perfectly you can call it around unity, but you can say it's a minus. In the sense power is minus, so power is fed to the grid. And this current is out certainly out of the phase. You are just seeing this angle probably 150 degree because the reason being that is a line voltage and typically the line current. So I mean that's the reason you just otherwise it's a perfect unity here typically like in and TAD of the of course current is not more than 2.6% even for different current level also. So that's about typically, and this is of course the again the single stage system. Of course, that was typically we reduce. It's a direct torque control, but we reduce the number of sensors. Like so what I asked this my PhD student that we don't want the sensor more than what we have in scalar control. So we are putting only two sensors, one current DC link current and one DC link voltage. From that only we are doing MPPT. And from this current, we are estimating this winding current. We are estimating the here voltage also. Only from this voltage and current, typically from the switching. So you can just clearly see it here. I mean from DC link voltage and DC link current, we are estimating the winding current here typically. And from DC link voltage, we are estimating the voltage also. And from this, we are typically going to be like a in a control with the torque, typically the torque, estimated torque here and estimated flux here, and it's running the drive with the your DTC mode, but sensors are only two. And that is only for PV. There is no sensor on motor side. I mean, like typically the paper is published in IEEE transaction of power electronics, so we don't have any sensor. There was a very interesting question if there is a long cable. I mean, like you have to put kind of filter there, whether this scheme will work filter or not. So we are able to successfully operate with the even a filter we put it with a long cable like a small LC filter here like also, so that there is no effect of like you can call it long cable on the motor performance also. So these are of course the equations for estimating the slip and estimating the synchronous speed and the rotary speed estimation on like also. And this is the concept of how we get the phase current construction from the typically coming from the DC link current like also. So this is a concept how it goes to typically for all like a different concept, but which current DC link current will be equivalent to which phase current and how it is there, the segment of DC link current. Like there is a lot of literature available. Like how to reconstruct in the DC side current of this inverter or converter to the AC side current. So we use the same concept so that the current sensor is only on DC link side. But of course, it was after the capacitor. Like, so this is corresponding to MPPT. Of course, at different solar intensity like 1000 watt and 500 watt per meter square. And then of course we have a starting like corresponding to both solar and solar 1000 watt per meter square and 500 watt per meter square. So you can just see satisfactory starting typically of this on motor winding current like your PV current as well as typically of the speed of the motor and the steady state like typically the currents on the motor side also like and all the parameters for different intensity, change of intensity, how the dynamics is there also of this case like also, and how it is typically the interruption there typically like. So that's about the induction motor. Like I think we already put more than 1 hour like but I thought it okay first motor. It's okay. Shall I continue? Hello? Hello? Is going okay? Rupak, anybody there? Hello? I'm like, no, I think all are. So anyhow, this is the second motor. We call it like a permanent brushless DC motor. These are manufactured, of course, also for submersible pump. And normally, on lower rating, the benefit of on lower rating is its efficiency is quite good. Like, well, so here we use little different concept. In permanent brushless DC motor, what we have here, we have a trapezoidal back EMF, so we have to put here the winding current as a rectangular current line. Okay, so there are two ways of controlling it of this motor. Either you control this voltage by operating this in PWM mode, means pulse width modulated mode, this inverter, and regulate this current into quasi square wave current like a 120-degree pulse current and magnitude zone changing depending upon the power and torque. And another way is that you operate the inverter in electronic combination with the Hall sensor and regulate the DC and control the DC link voltage. So we use both the concept here. What we did here, we use this buck boost converter, and this buck boost converter is responsible for MPPT, maximum power tracking of the solar, by changing the duty cycle. The benefit there are. Hello, Professor Jagdi?
Yes, sir. It's okay, sir. It's okay.
Okay. So we have a buck boost converter. The benefit of taking buck boost converter is that your PV voltage may be lower or higher. I mean, even if it is going to lower, you can have a boosting of it. If it is on higher, you can buck it. Okay, so you can select the PV voltage in a manner, and you can start this because it's a buck boost converter. You can start from 0 voltage on the DC link and start the motor in soft start. What we are not using any current sensor on motor side. We are not putting any voltage sensors also on this side. What we have only one voltage sensor and current sensor only on PV for MPPT. Otherwise, there is no other sensor. Of course, position sensor are there. Later on, this system is able to do sensorless of position sensor also. That's a different issue. But only it is a 2 sensor on here. And the motor runs. The another benefit is this is the only switch which is running with the higher frequency in PWM mode. This is not running in PWM mode. They are running only as a electronic commutation, means they are giving only the pulses of 120 degree for which switch, which set of the switch, like you can think about 120 degree mode of operation of the inverter. Like the losses in the inverter are drastically reduced here because they run typically starting from like starting from 0 frequency, it goes to like a 50 hertz or 60 hertz only. That is the switching frequency of it. Why the polarity change? Because the DC-DC converter will give opposite polarity. This will be plus and this will be minus. By the buck boost converter like that. So there is a novelty here that we reduce the number of sensors and we reduce the losses in the inverter also. Only one device operates at high frequency, like we designed corresponding to 20 kilohertz, so that the size of this inductor is also quite low. Here. Also, of course, we put some capacitor here because PV current will be continuous. And this is the inverter capacitor. So that's a BLDC. Of course, we use the DC-DC converter for MPPT as well as it go on changing the voltage accordingly as the power is more. It go on adjusting the voltage as the how much is the current required and the torque required in the pump. So a lot of interesting concept which I have to discuss first time with my PhD student, and it was even sometime finding difficult to understand. But I told, yes, this is the way you can think about. Like, okay, MPPT is a motor consumes the different amount of power and develop the torque indirectly also. So quite sensor and we took a motor of 1.2 whatever was available also in this motor, and these equations. I have MPPT of the solar here on the solar simulator what we have in the lab. It's working quite okay, like without any problem. And this steady state waveform correspond to different solar level. Like 1000 watt per meter square. You can see your winding current and typically the speed of the motor. And of course the buck boost converter and PV side data and the getting signal and all that of this, how it is going to be like. Typically starting, you can think about the starting winding current, how it is going up. Slowly like a PV current and typically DC link voltage. And you have a typically like a DC link voltage. Here you start from 0 because you want to start from PV voltage may be high, but the DC link voltage may start from 0 because it's a DC-DC boost converter. It gives from 0 voltage, it can go higher than input voltage also. So that's the benefit. How it goes from even a solar insolation level also, it is able to start the motor and run the motor successfully, even maybe lower discharge like that. So that's about like a typically, the change of insulation level, it works very satisfactorily. We have seen that what should be the typically the PV power, motor power, and the efficiency, and how it goes like with the maximum power tracking for this. Then of course we have gone to single stage. On this single stage, okay, we are putting of course only the sensor here, PV sensor, and see there is no sensor on this side here or on this side here. Okay. So we are doing MPPT here. The MPPT decides the duty cycle of pendulum switching of this inverter. I mean, like, and of course we end it with the Hall signals. So these are again gated for within 120 degree, but with the P and the duty cycle decided by PV array, as you might be seeing in the fan. Same concept is used here. But the benefit of here is we are able to reduce the size of electrolytic capacitor. We reduce as much as like maybe like a typically for this motor only order of like 100 microfarad, even lesser than that typically of this line. And the system runs very satisfactory without any one problem. Like of course the work was reported in this IEEE journal. I mean of this like also. So I mean this is MPPT corresponding to we decide the duty cycle of this and we do with the encoder signal getting and it's with the duty cycle of this MPPT decide correspond to that and do the ending with that. That's all very simple concept like these are all signal decoding for 120 degree pulse duration or so. And this is of course the MPPT correspond to 2000 watt per meter square and 200 watt per meter square. And of course your back cam typically the back cam then the winding current, EV voltage, I mean your Hall sensors like typically getting signals and I mean like all PV side voltage and current like also. And you can just see how it is like a typically winding current, practical winding current and decoder and how the getting signal finally. You can see the getting signal for the devices like how it is with the of course with the different duty cycle here during when the device supposed to I mean like to be gated like not all the time. So soft starting is also there because you are deciding the duty cycle for some to initially to start softly because winding current or PV current does not go to be very high. So it is under your control and then speed increases finally to go to MPPT also at different watt per meter square also and then insulation level change also. And then we look into efficiency and it give around 85.6% efficiency, very good efficiency of this system like also. And of course this is something how we just compare the scheme different schemes like. This is the case of again two-stage classical concept like okay. Boost converter what we used earlier for typically for induction motor, boost converter for MPPT, and then we have a getting signal here of course but here we have a sensorless, so we are sensing the back EMF and deriving the getting signal so that mechanical sensor is eliminated from here like in that case. Of course we have to sense line voltage, then the back EMF, then we have to use the low pass filter, then we have lead compensate because there will be delay in this, and then we have to generate the signal corresponding to and getting signal corresponding to that here typically. So that's typically the sensorless, which is again, of course, reported in the journal paper. We have a patent also, of course, couple of patents in this like. So this is corresponding to MPPT, and this is you can think about like a sensorless initially starting, aligning, then the soft starting and final running. Once the motor starts, it's able to run the respective without much problem. Like at both the intensity, when 1000 watt per meter square as well as 200 watt per meter square. Steady state result for both intensity like winding current and all those data, and corresponding to here also at lower intensity of the sun like, and then your change of the insulation level from 900 to 400 to 7, 900 to 600 also like that. And here also, I mean the same scheme we are able to put the grid also along with it. Because you like to have an uninterrupted water pumping, so some power comes from here, some power comes from the grid. So that scheme which you already talk about in induction motor, we are able to probably scale up here also in this case. Like so, this is DC link voltage control, which you talk about, and we get inductor current, and then we give the gated signal to boost converter. Also, design part and data of the system. Then of course the MPPT, and then of course you can understand the grid voltage, grid current. They are in phase. Power is coming from the this and power coming. Some power is coming from insulation from there, and we are able to get power factor unity here, like you can think about. So, I mean, power is coming from both the sources, solar as well as grid, like, and the supplement, like. So, winding current and the grid voltage, grid current, winding current, and of course the speed. Then the boost converter data and the power from the grid, how much it is coming, and the TAD, of course, winding current. Power factor is again close to unity, typically also. And of course, it's you can just see when typically the insulation is increasing, PV power is coming, then the grid current reducing, like, or here when power is reducing, the grid current is start increasing also, like, but speed is not much affected, only doing dynamics also. Other motor runs almost at typically same speed or something like that. But when grid fails, it runs only PV, so speed will go down. Like. So all the modes we have run it, suddenly grid fails, still you are able to run the pump, but of course at reduced speed depends on solar insulation. So, And this is of course the starting, which I mean you can see the winding current and then typically the speed how it is started like software. Then we have the scheme with the bidirectional power flow, because the BLDC normally of lower rating, so we can feed power here as well as we can take power from there, or we can feed the power to the grid. Like if it is a small system, like maybe typically single phase grid can be used up to typically a 4 kilowatt. So if you have a motor even of 5 HP, you can run well. Otherwise 3 HP, 1 HP, 2 HP, you can run very well power. You can have a solar panel of high rating and can feed the power to the grid. When pumping is not required, or you have a solar generation more. I mean, so it can be. Otherwise, in the night you can take power from here, or in the evening you can take some power from here, some power here. So you can have a bidirectional power flow control here also with the single phase grid. Also, this is about control of this bidirectional converter outruns. These are the data, and you can just clearly see it. Intensity reduces, power coming from the grid to run the pump, and but pumps almost at typically at constant speed is the effect of that. And these are the, of course, the grid current, grid voltage, grid current, winding current, and typically your uh, speed like. And typically the power factor is close to unity. You just see here with the TID 2.9% also. And then typically of course if here you run, you suddenly typically stop the pumping. So how did that? Of course overshoot comes, and after that the power start going to the grid. You can say the phase, look, initially power was coming from the grid, and once your pump, you stop the pump, the power start going to the grid, like, and current goes out of the phase with the voltage, like, which is here. So it feeds the power to the grid like that. So that's about the second motor. Now we come to the third motor called switch lucknut motor. And this motor is quite interesting motor. I mean, like we have a several motor in our lab. We got manufactured by industry also. Like that motor is also with us. So this motor have a very interesting characteristic. Like we have a 4-phase motor, and in 4-phase we need only 4 devices. So here also we use the same concept as BLDC, that we can control the speed either pendulum of this here, so that the voltage and current is changed and torque is changed, or we can control the DC link voltage so that sensors are not there on this side. So we eliminated again the current sensor from this side. We change the voltage or control the voltage across DC link, and we of course use the buck boost converter so that you can start the voltage from zero to soft start it, and after that you go to MPPT. I mean first soft start and then go to MPPT, and there is no sensor on motor side except the position sensor. Same way as BLDC, but of course the current shape is quite different here. So that's about the typically the motor specification and how we run design of this system, and how the motors getting signals and all that produced by this. And this is of course the MPPT of this and soft starting. How it goes the starting, and you have a winding current and all that. And the DC link voltage varies, because DC link voltage varies from zero. PV voltage is there, but DC link voltage varies from zero. So the typically the intensity change, increase in intensity, decrease in intensity. So we are able to operate successfully in all modes. And you have a 4-phase winding current. I mean, they are of course phase shifted by 15 degrees for this 4-phase motor. And typically you have a speed as well as you have DC link voltage, all parameters there of this segmental results. Like, I mean, all are these segmental results, and how the converter and all that at 2 different solar intensity changes, like the parameters variation of this. Then we put in single stage here also. By MPPT, what we do? We do the pendulum switching of these 4 devices, but they have to be gated only during the period when the particular phase is to be excited for producing the torque. So it's a single stage system. We are able to run successfully without much problem. Like, I mean, this PhD student of Anil Misra is able to run successfully in single stage also, similar to like what we have in BLDC. Like, also. So the duty cycle of this gating signal decided by MPPT. So there is no sensor on this side except PV voltage and PV current sensing here. These are the data, and these are of course the result under steady state. You can see the typically the winding current. This is a neutral current typically of the converter, and of course the phase voltage and all those. So we are running the here typically in pendulum mode, because this is a duty cycle of gating signal also. This is half fraction, and these are the gating derived gating signal also. And you can just see clearly our full winding current, PV data, and all other motor speed and all those make success in all signal switching signal. And then you are starting at 600 watt per meter and 1000 watt per meter square, and then intensity change from 600 to this 1000 and 1000 to 600. I mean, how smoothly it changes the dynamic. Of course, in their dynamics is not major issue, like, because This inertia is also high, solar intensity is not changed so fast like also. Like only performance. So here also we put of course grid interface also, typically along with the solar. Solar is single stage and we put the grid interface by bidirectional power flow and it worked very well. Reported in item transaction of course, sustainable energy by. So that's about the concept, and this is typically the control, the voltage source converter control also, and of course feed forward term, all those what we talk about in other motors also same way we put it here also like. And MPPT for this system and soft starting. You can just see soft starting and finally steady state conditions, how the typically your winding current, then the neutral current, which is a combination push center point, then the voltage across the phase, then of course the DC voltage or PV voltage because it's and how the grid side. So you have a perfect close to unity TAD of around 4.1%, the grid voltage, grid current, and the winding current and speed of the motor like. And similarly 4.2 typically at no load like how the it is taking place like power fed to the grid or something like that. So when motor is stopped, power is start feeding to the grid. Like here, like. And typically like here the power initially coming from the grid, but solar intensity increases, the power coming from the grid reduces, but motor is not interrupted. You can just see the current and the speed is not except during dynamic, otherwise there is no change like so when the intensity reduces, the more power comes from the grid. When intensity increases, the power coming from the grid reduces, but motor speed and motor currents they are not changing much except during small dynamics like also. So there, so that is about typically the uh, third motor. This is fourth motor like a called PMS, a permanent sine fed motor. Like typically, like first student graduated and second is working, and they are able to work sensorless very well without any problem. So again, two stage, you have a boost converter, and it's a sine fed similar to induction motor, and then you have a typically the bidirectional converter running here, and we are able to have a switching. Like of course on this we are able to have more the sensorless control. Typically to reduce the cost like the reported in industrial and transaction like also. So that's about the control. We are able to have a like a vector control here. Like typically you can just see the vector control. We have like typically runs on the reference speed from PV or constant DC voltage, and because it's a grid connected also. So you can have a grid alone, or you can have a solar alone, or you can have a mix of two. From main order, the power will go to the. So all four modes are there. That is how the mode is changing like awesome. And speed estimation from the voltage sensing, DC voltage sensing, also current sensing. We just estimate the speed and position. So here position is also required to estimate the typically for this transformation like alpha beta to DQ transformation. And finally from this alpha beta to again ABC reference, and we put a space factor modulation here like DC link board is a controller, and we decide, of course, the getting of single phase converter like for bidirectional power flow. And this is MPPT 4000 and 500 watt per meter square. The soft starting of the motor. Of course, it runs very fast because inertia of the motor was very low, and this is steady state. Typically, the motor winding current like also, and all typically the grid voltage, grid current, and then the winding current like also and speed. So as the intensity reduces, the more power start coming from the grid. So it's a grid current, okay, but motor current and motor speed are not affected. Similarly, as the intensity increases, the less power coming from the grid because converter operates unity power factor, the current magnitude program using. Like, and the motor current and speed are not affected like also. Suddenly the solar is off, then the power start coming from the grid, and you will see winding current and motor speed are not affected at all. So dynamics is quite good. Like here, the suddenly PV insulation came, the winding current, motor current, grid current reduced almost go to zero, very low, and winding current and motor speed are not affected. So motor does not see any whether grid is coming or grid is not there, or solar is there or solar is not there. It worked very well. So you can just see the power factor close to unity, and TAD of the winding current is quite there. And here power is negative means power is going to the grid typically, and TAD is to 3.2% also. Here typically even the power gen fed to the grid condition. So that's about the fourth motor. Now this is the fifth and last motor. Like also. So typically this is the synchronous reluctance motor. You can just see how the rotor look like a very. In last 5 years only, the ABB launched this technology up to 300 horsepower, starting from probably half horsepower to 300 horsepower. And we also got developed the motor by the industry now. They have developed many motors. We have probably a couple of motors developed by industry also. With the whom we are doing work with the Shakti pump from Indore. on the industry. So here what we have again the boost converter, okay, with the solar, and then we have a typically running this motor. The concept is here. We say this increases the cost, this increases the complexity. The concept is that we have to eliminate these two, boost converter as well as this. Like that's the concept. I mean the guy put in this like so single stage. So boost converter is eliminated, and we are eliminating the typically the position sensor also, so estimation. So only winding current and PV voltage and PV current. So these are two sensor here, three current sensor and one voltage sensor is enough to run this. And this is the control where we have MPPT control, and then we have a reference speed estimation, then the from function and current we are able to estimate typically the position. Okay, position here. The interesting part we put it because the motor will be running at different speed and different. So we are able to adjust the flux level also, so that saturation is also change in the motor. Like so, interesting. We have to look into because this motor is not so popular, but recently it has come. So we are able to have a like even at lower. You can understand when we run with the lower solar insolation level, we run on lower speed, but it's not necessary to keep the flux constant. So we reduce the flux also, so that magnetizing current of this motor is reduced. So that's the concept we run in this case. Of course, this is a hardware setup the guy is working for. These are some of the benefit of this motor. The motor is quite high efficiency, of course, reduced cost and very simple control and quite robust. Like as far as construction is concerned, better than induction motor in efficiency. Power factor is a little poor than induction motor, but the power factor can be enhanced by reducing the flux in this depends on the solar intensity. Okay. So we use of course in vector control as well as you see here. Of course, vector control run very successfully without any problem. And this is of course we use the MPPT. Typically here also from the solar, of course it was single stage. So you have a this reference voltage from the MPPT and get this digital voltage controller, the one speed component. Another comes from the power F18 law, and we get the reference speed from there. So this reference speed finally get difference of the two icon also. Well, from speed controller we get the torque reference. So once we have a torque reference, from torque reference and ID we calculate here. ID there are many concepts. One is for power factor optimization. Another is the another concept is typically like you can keep a ID constant or you can vary the ID according to the torque developed by the motor. So many concepts are there for ID. And then once you know the ID from this torque, we are able to get IQ here. So once you know ID IQ, you can transform to three-phase AC current, and from using path transformation. So you have already the position estimated, and then you can have a current controller like. So it's a different solar insolation level. You have a MPPT of this. Like typically working here, and this is you can think about like a starting performance. Okay, typically here and typically after starting you have a because it's a sensorless. So first we have to have a open loop starting, then it go to like an MPPT tagging and work very well satisfactory without any much problem. So this is typically you can three-phase, three-phase winding current and speed, and here PV voltage, PV current. Because it's a single stage system, and you have a speed and then the motor current like at 800 watt per meter square. And this is of course the how we estimate the typically the flux and position. So this is 5D and 5D and 5Q in stationary reference frame, then the net flux, and 5D 5Q plotted in typically on the CRO you get holograph, and if it is a circle, complete circle, it means these are sinusoidal waveform like. So from these only we are getting the position, and from position we are getting the speed, virtually for control and as well as for the purpose this position and speed we use for the purpose of control. So this is when intensity change. Solar intensity decrease, how your frequency and speed of the motor reduces because you have a less power now. Like typically how it is going to be decreasing solar insolation level also. And then when solar intensity increases, how your frequency and speed are increasing like typically here also. Well, this is another concept that typically the student put it like what is the typically the mechanical power and efficiency concept like typically here. And the cost issues because normally these students work on the when the reviewer of this good quality paper. So how much is the cost of particular element in this also different part. Now another next is the like a bidirectional. Bidirectional means We have a three-phase supply. Considering that motor rating is substantial, so we have a three-phase supply. We have a PB with the boost converter. If pump is not running, power will go to the grid. And this PV array rating is much higher, and some power go to the pump, some power go to the grid. And of course, when pumping is not there, total power can go to the grid. And if intensity is less, some power comes from air, some power comes from air. And if there is no grid, you can run with the solar. If there is no solar, you can run with the grid. So you get uninterruptible water pumping here, provided grid is there. If grid is not there, you have to run corresponding to whatever the solar intensity is there. So it runs satisfactorily in all modes. This is the typically control how we do MPPT, how the converter control, typically, and how the motor control typically for sensorless operation. All are here typically. So you have ID, IQ. IQ get torque, and from ID from here, you have a position estimation as well as from speed estimation, and you have a transformation from ID IQ to your ABC, and then getting signal. You have sense current, reference current, and then you are getting signal for the AC control like that. Well, again, the mode is same. When grid supply is not there, only you run from the solar. When there is no solar, you run only from the grid. And when both are there, sharing, and when the pump is not running, it goes to the grid like also. So this is typically the rating of the system, PV rating, motor rating, like motor what we procure from ABB. Of course, the next system is working with the industry motors, like that GERD is working. So this is corresponding to MPPT, and we have some time of MPPT also. Like in for some mode you can run it. Like typically in that case, like. So this is typically the starting, safe starting, or you can call it like a soft starting. Winding current is not going to be in any way going to be more than particular. That's also inverter current like output. And this is typically again the soft starting, how it is like change from initially starting to the final running. Like it's not a very major challenge. Very simple sensorless also work here because it's not a very precise kind of application. Like it takes a little longer time. Also, it does not matter. Like so, these are the steady state. Okay, typically the winding current and the PV voltage, PV current and speed, and these are position estimated. From here, typically, like also, and then you have a like if intensity reduces, how the current in the motor are reducing, like your speed is reducing. Like here, different parameters are changing during the dynamics, like also, and when intensity is increasing, how it is increasing the current and typically the speed of the motor, and other parameters also, how it is running, like typically the grid current and all. This is how the grid power is taken from the grid. It's coming typically here, and you can just clearly see here how the typically the TAD is maintained of the even a body TAD 2%, 2.6%, but current TAD is 1.7% only also. And how the power like typically when you can just see the starting and power is sharing from it's starting from the grid mode also. Mode 2 means only from the grid. Mode 3 means they are sharing power from the grid as well as solar. And mode is that power is fed to the typically from the even to the grid also, apart from motor running like that. So these are typically you can see the power is fed to the grid, so current is out of the phase from the voltage like typically also. So it runs very successfully. Like with the power is minus means power is fed to the grid like in that case, because solar is taken off high rating or pump is not running in that case, like in both the cases or otherwise like. And how it is like a typically the mode changing, from third mode to fourth mode and fourth mode to third mode. So typically how the solar intensity changing, and accordingly the mode is also transiting from one mode to the another mode in automated fashion. When the grid goes, like you just don't see the any effect typically. It goes to then solar mode, so maybe whatever power accordingly speed is adjusted for. Like when solar goes, then how the grid automatically increases the current also. Both of them. So this is about like what we have. We have the project little bit. What I told you about the typically in this project, what was the objective? We have to develop all 5 motors with a 5-star rating and their controller also. And of course, this is the justification about the project. Then what methodology we adopted, and these are the motor photographs. Like you can see one they are manufacturing like a PMLDC motor, then synchronous reluctance motor, which are developed at Shakti Pump, like, and then the typically the your PMSM and C reluctance motor, and of course the induction motor. So all 5 motors are manufactured by the industry, and we have taught certainly one piece in the laboratory, and they are tested with the sort of pumping system. Of course, induction motor got developed by our another industry also. That guy is able to increase around 10% efficiency in 1 HP or 2 HP or up to 3 HP motor in induction motor also with copper bar, obviously with a copper bar and copper design or something like that. Because these are inverter fed machines, so we are not bothered even induction motion as far as the starting concerned. Right? So you can just clearly see how the synchronous reluctance motor, how the PMSM, how the reluctance motor, and how your PMLDC, I mean the different parts look like during manufacturing also. And of course, with this, I would like to probably, this is how commercializing the technology. With this, I would like to conclude. Like, I mean, typically, I think it goes with the time not so bad. Okay, so we develop all five motors, not only the controller but the motors also, and tested the motors successfully without any problem. We have it so far, typically the 12 patents. I mean, of course, not all motors are equal patent. We have a 12 patents coming out with this technology, and we have a typically like a, I think 48 journal papers, and we have a 52, typically I think 52 conference papers. So 100 papers with 12 patents. I mean, that's the technology what by developed, like I think conference papers are more. Typically 86 conference, 48 journal, and 12 patents. So if you have any query, I will be happy to answer. Like, yes, Professor Jagdish, I mean, like, ball is in your court.
Okay, sir.
Department faculty may
Participant, please ask question. Hello, sir.
Sir, this is Dr. Prem from GMR, Andhra Pradesh.
Yeah.
Sir, can you hear me, sir?
I can listen to you. I can hear you. Okay. I cannot see you. I can hear you.
Yeah, okay. So the thing is, whatever the paper you presented, only have done with Hello.
Hello. Yeah. Can you put
Sir,
your?
we have tested everything with the order of observation and incremental conductance algorithm, right, sir?
These are all experimental results we put it. We have not put any simulation results. Okay.
Well, that is what my question is. Why it is not tested with any global MPPT techniques?
Global MPPT. Because the pump are always in a place where we don't have anyhow. I mean, these students have not focused on towards MPPT. We have another set of students. We have on MPPT. We tested all global also. I mean, like here's a 10. Virtually, you will find 10 transaction only on MPPT. Okay. So
Yeah.
they are exposed. So they are using a different MPPT. I'm not talk about too much about the MPPT, but they have used the different MPPT technique. Not only like a maybe some student use the modified this perturb observe, like called drift free MPPT. So I'm not stressed too much on MPPT because the more stress was on probably on drive. But we have tested with many MPPT, not confined only incremental as well as only your perturb observe. So we tested modified incremental as well as modified, I mean your perturb observe also. And we have used many your even a heuristic technique, global technique also. Many my students have. So you can look into probably Dr. Nishant paper. I mean, he has a more than dozen paper on MPPT only. Okay.
Okay, sir. Yeah.
Hello.
Yes.
Hello, sir. Good afternoon.
Good afternoon.
I have one question. In one of the example which you have given for synchronous reluctance motor, you haven't used the boost converter.
Yes.
Whether basically for that drive some extra control technique will be required if we not use this boost converter.
You are talking about boost converter for solar MPPT?
Yes.
The very purpose is that I mean for MPPT, normally in a such system we like to maintain the DC link voltage constant.
Yes.
Okay. So once DC link voltage is constant, then the boost converter have to do MPPT, because you cannot do the two tasks from the inverter. I hope.
Okay.
Okay. So two tasks in the sense I'm talking about, either you can regulate the DC link voltage or you can do MPPT. Okay, by the inverter. So both cannot be done.
Okay.
DC link voltage then have to be decided by the design of PV array. Okay, how you are designing it, what voltage you are.
Yes. That will be decided by PV array then.
Then PV array, design of PV array means how you are selecting PV array voltage corresponding to MPPT.
Yes.
So
Okay.
then DC link voltage will vary within certain range. Are you able to- But if you want that the motor should be almost like a operation should be almost like isolated from PV side, irrespective of the PV, which there was a question previously, na, like why you don't put a like a global MPPT or something like that. Then if you have a partial setting or like a cloud say, in that case, DC link voltage can be maintained. Even the PV voltage may go down. So boost converter can do that job. Are you able to follow?
Yes. And second question is, sir, whether multi-level inverters can be introduced in this?
Multi-level inverter can be beneficial on the two side. One is on motor side.
Okay.
Okay, when you want to have your common mode voltage reduction, like, and the rating is high. I mean, the multi-level, I have another couple of PhD students. He did on multi-level. I mean, I told you, because in India, all the NITs and many IITs, I mean, many people in the country, they are working on
multi-level. Yes, sir.
I can tell you, I mean, I have been a little pessimistic starter, but we are a very aggressive researcher. So once we start some technology, within 5 years, we don't want to become number 2 in the world.
Okay, sir. Thank you, sir. Thank you very much.
Go to multi-level, but one of my PhD students who came from NIT, he says, I want to work on multi-level. Look, you are going to commit suicide, man. I don't have any project. Okay?
Yes.
Typically, you will not believe I have to manage around 60 lakh from other project for getting a multi-level. Of course, he finished the PhD. He has joined after submitting the PhD, his Viva is not over. He joined the Day-4. He did good work. I mean, and now another PhD student, of course, took over. And I wanted probably to put. So he's working with the induction motor, but certainly all these are medium rating. You can call it medium rating, means megawatt rating.
Okay.
Like for low rating, your multi-level is not. Even a submersible water pumping, what we use, even if it is 100, 200 feet down in the ground, you have a long cable. So we normally put a small filter. Okay, small filter after the inverter. Okay. Not very high size, very small, because you have been in touch with the industry also, because industry can't run the product without product. So
yes, sir. You have told in the beginning only that when cable length is more, we have to introduce a filter there.
Even without even a long cable, also some small filters the industry put it, but they don't talk about, nobody talks about that. But when we touch in the industry, I mean, we have to take all those aspects. This is more insight when we wanted to have a sensor reduction.
Okay. Thank you, sir. Thank you very much.
Sensor on motorcycle, current sensor, we put on DC current sensor and voltage sensor also. So question was whether your engine will work with the filter also or not. We have to put filter and just so yes, it will work with the filter also. Multi-level is normally for higher rating, and I don't expect solar water pumping is a very high rating. It may not be good more than 25 horsepower or something like that. Multi-level inverter is always considered not less than typically a megawatt rating.
Yes, sir.
I mean, that's the reason I can tell you like why multi-level. I mean, like we work with solar water pump. We work with the multi-level to grid interface. I have probably on solar grid interface. I mean, I graduated around 10 PhD students and maybe they are working. We have a big funding on solar grid interface also. So that could be around 15 to 20 crore. I'm converging the project line. Funding as high as maybe around 5 crore, like at a time. Converging, I have to finish up to next year. 70 PhD students are working, 84 already graduated. Like,
yes, sir. Yes.
And this lockdown have made me busy. I can tell you.
Yes, sir.
Every day I have to clear 1 to 5 papers every day now.
Okay.
Hello. Good afternoon, sir.
Any other question?
Sir, good afternoon, sir.
Good afternoon.
Sir, among the 5 motors, which motor is suitable for the agriculture purpose, sir? With low cost.
You of course will ask from the doctor that which medicines will be there. You can understand that why we work in the motor, we should see the benefit after this is very interesting.
Sir, every motor it has its own efficiency and own benefits, sir. But as per the agriculture people, how they can take as a best way, best output form, sir.
No, if you have a very low rating, na, like a half HP, you are using for drinking water supply, pumping. Okay, very little pump for drinking power supply. Maybe you might have seen a half HP motor, quarter power. Such a small rating, obviously the permanent buster DC motor is the one of the best. Okay. And we were giving full induction motor efficiency improvement also because you should be able to reduce without increasing the cost. You should be able to reduce improve the product. Like so, concept even in induction motor, what we did, we increased the efficiency in 1 HP, 2 HP, 3 HP around 10%. So panel size reduced by around 30%. Okay. So very soon, I will suggest like what we do, DC motor is quite good. Because its efficiency is quite high, so panel size will reduce it. Okay.
Okay. Thank you.
Available also and easily can be manufactured also. That when we make it with the ferrite magnet which are available in the country, it's quite okay. But many people believe that permanents are available only in China. So you can the motor like what we can call it like a switch lectern or that all 5 motors, especially all the synchronous reluctance and switch reluctance motor also should be manufactured by the industry and all 5 motors.
Okay. Thank you, sir.
That's any other question?
Hello.
Yes.
సెకండ్స్ 400 ఉంటదండి.
Hello.
Yes.
Good afternoon, sir. Hello.
Hello. Yeah.
Good afternoon, sir. Sir, I want to know what is the research in recent MPPT techniques.
What is the research in MPPT exactly? By every day research is also very challenging. Couple of he was more in background in power system. So he talk about lot of algorithms. These algorithms called heuristic algorithm or bio-inspired algorithm.
Okay.
Optimization, I don't know which kind I have to learn from. By going through his paper, I have to learn, then only I can clear it. I have to see my own hardware also. Without that, I cannot see. Show me the implementation. So he has a lot of like whale optimization. Particle of course, particle is very old. Then on colony, all those algorithms we use it practically in the system. And you can understand it was very interesting. When we communicated the paper, you know what the reviewer asked. He claimed that the algorithm is fast so that you don't put the energy.
Okay.
What the reviewer asked, he said, please take the video and put on YouTube and give me the address. Neither he or she knows our or we don't know the reviewer. You have to give a video, and after seeing the video, he is just clearing our paper because only on XY on paper you cannot put the result like of dynamics results are able to follow. And this is the interesting experience. Like I student have to make a video and put on YouTube. Very classified, and we pass on link as well as password, and the people is able to see it. These were the couple of journals which were neither our identity was disclosed nor their identity was disclosed, like IEEE transaction on industrial electronics, IEEE transaction on industrial informatics.
Okay, sir. Okay. Thank you.
Sir, I have a query.
Yeah.
Sir, you have suppose for induction motors in single two-stage by Saurabh Shukla, there are no batteries in between that, and I don't know how it can regulate the DC voltage without any battery support.
We are regulating the DC link voltage by control.
The capacitor should be quite larger, sir, for this.
No, not necessary. No.
So is it able to bear that?
No. You might have seen a loop. We are putting another closed loop like a PI controller for regulating the DC link voltage. In two-stage, we always regulated the DC link voltage. It's not necessary. Of course, some student put the battery also, which I have not shown today presentation. I mean, they have a battery also they put. It's not like we have not put the battery in the research, like, but the cost will increase. And battery is so costly, you can't think about the farmer. The poor farmer can't maintain the battery cost, size, weight, and theft. More important is that. I mean, like, so, well, we put the battery also, but of course, for some cases, but not. We prefer to run without even sometime we have to run the grid is not on. It's like a standalone. You are far flung area.
Sir, if the input is an AC supply, then I agree because it is a stiff source and it can make that capacitor voltage fine. But the input is solar PV, so it's going to have a drop in its voltage. And I have seen that it is in your results, it is almost stable. The VDC is almost stable. That's the thing.
We are using a boost converter, and the DC link we are regulating the DC link voltage by proper control. I mean, this is a concept which I have given to my student. Like, even for that student, most of the student it was difficult to make them to understand. Think about all the AC motors, whether you take an induction motor, or you take a permanent synchronous motor, or you take a synchronous reluctance motor. They are a sine-fed motor. For sine-fed motor, you have to maintain some amount of DC link voltage. Then only they will be able to produce the sine wave current properly in the winding of the motor. So for those motors, we have to maintain some amount of DC link voltage, certainly. So in those motors, we prefer to obviously keep a DC link voltage constant by putting a boost converter for MPPT. But boost converter cannot do two tasks. It can do either MPPT or it can regulate the DC link voltage. So DC link voltage we indirectly control by controlling the speed of the motor. Are able to follow? Like, if you have a more power, the speed will increase, but DC link will be regulated. If the less power, then the speed will decrease. From DC link, you take a less power and regulate the DC link voltage. Once the control is there, you know to increase the capacitor size. So control takes care of it. Them also it took time to understand. But since I have worked on many other technology, how the DC link voltage is regulated with the closed loop, how the overshoot can be avoided, undershoot can be avoided, like with the proper control, a lot of DC link voltage control was not an issue. I mean, in one case, in some cases, we are able to reduce the capacitance value quite small.
Yes.
Particularly, there was a question on one recent student on induction motor. I mean, she is not able to, of course, the student is not able to follow, and then we are able to reduce the capacitor even for like typically on 3 horsepower, only DC link capacitor of around 100 microfarad, or even less. It can be less than that. You can reduce the DC capacitor to much less. I mean, like in a typically like a reactive power compensator, like your active filter. Typically, those who are able to only generating reactive power, you can reduce there. I mean, Akagi in 1984, I have demonstrated that 4 microfarad is enough on DC link for 3-phase inverter to generate the 20 ampere AC side current. So when you have a 3-phase balance current, either from induction motor or PMSM or synchronous reluctance on AC side, DC link capacitance can be reduced quite small. I can tell you, there is no issue. Okay, control. Okay, but that's a altogether different research. Okay.
Sir, and even for a single stage, a low value of capacitance is fine.
Yeah, single stage also there is no issue. Try to understand, like, you are not getting what kind of ripple you are getting in the DC link. If you have a 3-phase sinusoidal current going into the motor winding, only the ripple will be corresponding to switching frequency because of the diode conduction, freewheeling diode conduction. That will be of switching frequency. Might be 20 kilohertz or 10 kilohertz. Same way, you are having PC side you are not putting anything. So the ripple current will be of order of even if inverter you are operating 5 kilohertz or 20 kilohertz, the ripple will be of 20 kilohertz. Corresponding to 20 kilohertz, you require even a very small, maybe 5-10 microfarad or 100 microfarad, not more than that. So you can reduce the value quite small, provided you are not interfacing the single phase supply to it. You are only interfacing either the boost converter or no boost converter. Are able to follow. But motor current is balanced because you are running with the vector control or DDC units, it will be balanced. So capacitor is not a major issue. And here it is energy is not, look, what will increase in DC link? Maximum the PV, even if you are not running the motor, what will happen? The DC link capacitor voltage may be only equal to open circuit voltage of PV array, not more than that, for which you are designing it. Are you able to follow?
Yes, sir.
So there is no problem with that. Like.
And sir, and in most of the results, I have seen that for induction motor, the starting current is slowly increasing instead of large currents.
Because we are operating in we are operating in like a variable frequency type. Either scalar control with a low frequency starting, or vector control, or direct torque control. So once you operate like in a vector control, let us say you are operating this motor as like a DC motor. You can get the rated torque with the rated current, provided you regulate the frequency. If you have a frequency, let us say corresponding to like a slip frequency, like at starting, the stator frequency and rotor frequency is same. So if you have a like a say 5 hertz on rotor side, 5 hertz on stator side, 5
yes,
hertz
sir.
you need a very small voltage, and current cannot be, and you keep the rated like a concept of vector control or direct torque control or scalar control make your induction motor equivalent to a DC motor. And DC motor even at starting can give you rated torque with the rated current. So same concept is applied here. We are not connecting the motor directly to the grid. We are connecting through the inverter with power control. Just any other question?
And from the PV MPPT, you have generated the voltage VDC reference, and from there, you with the PI controller, you have taken a speed reference. But how can you say that the PI controller output is a speed?
The reason being, if I have a more power, I should run the motor on higher speed. Are you able to follow? Then only
yes,
it will
sir.
consume more power. Because it's a pump. Pump characteristic, let us say you have a centrifugal pump. Your power is proportional to square cube. Are you able to follow? Torque is
Yes, sir.
square proportional. So if you really run on pump means indirectly the motor, if you run on higher speed, then only it will consume more power.
Yes, sir.
Are you able to follow? It's just like a basic concept to understand. I mean, like, so if you want to consume more power by pump or motor, you have to run little on a higher speed, and that's the reference is between decided by the power. So same affinity law we are using on PV side. From PV power, we are calculating the reference speed. Are you able to follow? By same
sir.
cube law. Even if we put like law or the closed loop control is a physical system. We have to understand the basic physics of the motor and pump. As the speed increases, it will consume the more is power as the speed increases. I hope it is clear. Like,
Yes,
okay.
sir.
Sir,
And I have a
respected sir.
query between.
Yes.
I have a query between standalone and grid integrated. Sir, in the standalone single stage, suppose whatever the maximum power that was developed with MPPT, that is given to induction motor. Whereas in case of both grid and PV mode to induction motor, how the power sharing can be done? It's like we don't know. It's like the
No,
maximum power that is being.
No, when you have a, let's say you want to run the motor with both the sources, your interest is that you have to run the motor at full volume and full speed and full rated power. Are you able to follow? So you
Yes,
keep
sir.
a reference speed rated, and then it does and regulate the DC link voltage with the help of these two converters. MPPT will put the maximum power whatever it can do by boost converter. Clear? Or
Yes,
you
sir.
regulate the DC link voltage. You regulate the DC link voltage in such a manner that PV have to generate the maximum power.
Okay, sir.
Have to come from the grid. Are you able to follow? You are talking single stage connected to grid as well as the. Is there any other question, Professor Jagdish? Like,
No, sir. Sir, can I say something with your due permission? Sir?
yeah, go ahead.
Okay, sir. Thank you, sir. Sir, I Jagdish Chaudhary on behalf of the Department of Electrical Engineering, Nagpur Institute of Technology, Nagpur, and entire team of Faculty Development Program and all technical fraternity of electrical field here together, participants, and on my own behalf, extend very hearty thanks to respected Professor Bhim Singh sir for gracing his important work in the area of control of brushless motor for solar water pumping and sharing with us various findings meticulously explained through nice presentation, exhaustive presentation, I will say, and focusing on all 5 motors: induction motor, BLDC motor, switch reluctance motor, synchronous reluctance motor, and SRM. Sir, I am very much thankful to you, sir, for accepting our invitation and exhaustively, continuously talking for 2 hours and giving more thoughts, more pinpoint for research area for new researchers. Thanks a lot, sir. I am also thankful to all participants and research scholars for attending the session patiently. Thanks one and all participated in today's technical talk. My sincere thanks to my techno-savvy team of electrical engineering. Sir, thank you very much for accepting our invitation and gracing this session very nicely and very helpful to each and every participant. Thank you one and all. Thank you very much, sir.
Oh, thank you, Pastor Jagdish. Can I leave now?
Yes, sir. Thanks a lot. Have a good day, sir.
Okay, good day. Thank you very much.
Okay, sir. Thank you, sir.
Okay.
So thank you, all of you. Thank you, sir.
Thank you, all participants.
Thank you.
Thank you, sir.
Thank you very much, sir.
Thank you. Thank you for your patience listening. One last day, we are just tomorrow having a Vinay Kumar sir session from NIT Warangal.
Thank you for conducting this type of program, FDPs.
Feedback and attendance, everything is sending through your WhatsApp group, right? Please give through that.
Thank you very much, sir, for conducting this type of FDPs.
No. It's my pleasure and it's a cooperation from all of you participants.
Okay, sir. Thank you very much. Thanks a lot, sir.
Sir, from my side, I have small request, sir. Sir, I didn't give attendance last 2 days.
Okay. No, attendance problem. Attendance we are circulating. Okay. We are taking final feedback. Then you just give feedback for all sessions, right?
Feedback, I guess. Okay.
Hello. That we are circulating through group, sir. Through WhatsApp group.
Hello. Good afternoon, sir.
बोलिए sir. बोलिए. Please बोलिए.
Sir, please switch off the chat box, sir, while presenting. This is unnecessarily irritating.
Okay. We will
after the presentation, you will enable the chat box for question and answer section. It is unnecessary, and so unnecessary. They are posting nice presentation. All you know that nice presentation going on.
No issue.
What is the meaning of that? Writing nice presentation.
We will take care tomorrow. Okay. Thanks for your suggestion.
Thank you, sir. Okay, sir.